I guess. Okay, I put a couple of things up on the board. I'm using yellow chalk today because the white chalk seems to be out. So I guess you can see what I wrote up there. And I want to talk first about over here on this side. Morning. Guess before I go further, let me ask, well, I've got most of you. I asked a little earlier, a couple people came in. I extended the WebAssign due dates on all the 7. Some people had asked me to do that. I don't know if I responded to all of you who asked, but I went ahead and did that. The question is, when you ask me to do that, do I need to send you an email back? In other words, how often do you check it? Do you check it enough that I don't need to send it back to you? Okay, because I got lots, I get between 100 and 200 emails a day. And everybody wants me to respond in one way or another. Not everybody, but hi. My secretary, I guess, proving that she's here. Anyway, so if I extend the date, you guys just look and see. And if I haven't extended a while, write me again and say, hey, I thought I asked you to, you know. Of course, I won't always agree to your request, but so far I did this time. Okay, so I'm hoping, I think I extended it to Saturday or something first. I hope that's long enough. 2 integrals here that you know how to do. One is the integral of 1 over x. The picture of the 1 over x is, it comes down like this, you know. It's a positive thing. And the t here is some number. And this represents, I don't want to mess it up here, but the inside here represents the area given by this number, whatever the t is. Now t, when you see t, a lot of times you think it's a variable, but t could be 10, for example. And if that was 10, then basically we would have a log of 10, and that's the area under the curve. You know that. Okay. If I do the same thing with 1 over x squared, and I draw a picture, and I change the 1 here just to make it more visible. If I do the same thing, trying to copy the same idea here, they both go through 1, and 1 over x squared looks like this. And if you go to t, you get the area under the curve, and this time is 1 minus 1 over t. Okay, fine. So the question is, what happens to the area as t gets bigger and bigger and bigger? Now, the log function itself, as you know, looks like this, and it just keeps going up. So as t gets bigger and bigger, the log gets bigger and bigger. So the area under here, as t grows, gets bigger and bigger and bigger. Okay. After a while, it'll double, and then it'll triple, and it'll quadruple, and so on. This area, as t gets bigger, subtracts less and less from 1. And therefore, the area under this curve is never as big as 1. So as t gets bigger, it grows, but it never grows higher than area 1. So the area in the second situation is bounded above. In real numbers, when you have something bigger than anything in a set, it's called bounded above the set. So the set of areas in this case is not bounded above. The set of areas in this case is bounded above. But when I drew it, I tried to draw it like the curves look. But, and if I did it, they look alike. And so basically, this human, and I think most humans, don't have any good feeling for what things here if I let the area go, if I let the t get bigger and bigger, which integrands are going to produce a finite area all the way along, and which integrands are going to produce an infinite area all the way along. I'm sorry, not an infinite, a bounded area. This is getting bigger, this is bounded. Which integrands produce those two behaviors? And as far as the graphs look, they don't look that much different. Now, if I put one graph on top of the other, what will you see? If I would superimpose this one on top of this one, then when I get out here, if t is like 2, then this is going to be height 1/2, and the other one is going to be height 1/4. So what's going to happen here, if I superimpose both graphs, one on top of the other, the one under here is going to have area less than 1, and the other one is going to have area that goes to infinity, but still humanly, it doesn't look like that's much different. And so our intuition is not very good. At least my intuition is not very good. Okay? So what's going on here? Well, I don't know, but whether or not, if I allow things to go bigger and bigger and bigger, whether or not the integral represents the area under a curve, we could discuss or argue about. Because if it goes into infinity and it keeps going, is there an area? It's kind of like open, kind of at one end, right? We don't usually think of infinity as a boundary. You sort of think of it, see, before 1870, people thought of infinity as going on and on and on. If I'm going to say there's an area under here, if I let t go to infinity, that's kind of like saying that's like a boundary. To make an area, you need to have an enclosed region, right? So whether it's area or not, I don't know. But what we do is we take the limit of this as t goes to infinity to see what we get. And if I take the limit here and I take the limit here as t goes to infinity, this is going to be plus infinity. And if I do the same thing down here, okay, same limit, after I get done doing all the work here, if I take the same limit going to infinity, in this case, I get 1. Now, so what we're doing is putting a limit together with an integral. But you know how to take limits roughly, and you know how to do integrals roughly. Therefore, this is not that big a deal. What we get is called an improper integral. And the notation we use for the top one up here will be from 1, and we write infinity on the top, 1 over x dx. This symbolism I'm putting on top, and as you guys know, I say every day, my space is my problem here in terms of making it visible to you guys, both home and here. This symbolism, and all it is a symbol, means the limit of this. And so now, of course, we don't need to have 1 over x there. We can have any f of x. All right. And this is called an improper integral. Now, it turns out that once we get into this game, there's 2 types, or maybe 3 types, depending on how we're going to do the third type. So later, we're going to call this an improper integral of type 1. But right now, since we only got 1 type, we don't know that yet. Okay? So what is part of the game in the section of the chapter, last section of the chapter, is to put different integrands into this mix and see what the answer is. When the limit exists, and that means a number, the improper integral is said to converge. And it converges to the number that's the limit. Okay? When the limit is infinity or doesn't exist for some reason, at all. And when I say doesn't exist, remember you can have things that don't exist and not be infinity. When limit doesn't exist, it's called divergent. So we have converge and diverge. Is a way of explaining to somebody that improper integral, what does it do? It converges. That doesn't tell you to what, but it tells you it does do something in terms of a limit being finite. Okay. So that's that. Now, there's nothing special about one. I just used one because it was convenient. So we will replace that with different integrands. So I'm going to put that here. We're going to be talking about things from a to infinity. And sometimes people put a plus here from infinity. We'll be talking about this thing, and this just means a limit. So when you see this, you know it's improper, because when you see an infinity, it's definitely improper. And what it means is a limit, and you put a letter here. Okay. Now, if you want the function to be a function of x, then I've got to change the x here to something else. Okay. For example, again, my space is my problem. For example, I could talk about the limit as x goes to infinity of f of d something, and I could make this a, and if I make x go to infinity, I would put the x up here, then this might be t. I can't use the same letter up here as in here. So if you want to have the answer, if I did that with this problem, it would be 1 minus 1 over x if I switched it. It doesn't matter what the function, what the independent variable's name is, as long as you realize it can't be the same name up here as you use down here. So if you start with an f of x, but you want to end up with an integral with something with x, then you need to change the integrand to something else. Or if you don't care, it's okay to have this, because really we're going to take a limit and get rid of it in the end. See, it doesn't exist in the end. So intermediary, whether it doesn't depend on which it is, as long as you are consistent. Now, okay, how about this one? Well, we know integration by parts now, supposedly. At least somebody did 50 problems in section 1 yesterday or the day before. Anyway, you should be able to get this answer. Okay, now, I don't care if this answer is right or wrong, really, right now, because I want to describe something else. What do you think the integral from, if I put minus infinity down here? What does this mean? Well, it means the limit where you put t on the bottom and t goes to minus infinity. Same idea. If you can go this way and deal with that, then you can go that way. Same idea. Okay. So that's, I hope, understandable. What happens in this particular problem? I didn't put the infinity here yet, but in this particular problem, what is the integral from 0 to minus infinity? Okay, it would be t goes to minus infinity. I'm going to take this answer. What happens to 1 minus t e to the t minus 1 as t goes to minus infinity? Well, this minus 1 doesn't hurt anybody. What happens to e to the t as t goes to minus infinity? Goes to 0. What happens to 1 minus t as t goes to minus infinity? Goes to infinity, plus infinity. So I have plus infinity times 0. What does that do for you? That's indeterminate. What do we do with indeterminates? We reviewed this. It's L'Hopital's rule. So all of a sudden here we got a L'Hopital's rule coming in, and it comes in a lot because now we're heading toward infinity. And so you're thinking about putting infinity into the mix. And so this is a place where L'Hopital's rule gets used. Anyway, what you would need to do here is instead of infinity times 0, we need to make it infinity over infinity or 0 over 0. And you can, anyway, this turns out to go to 0, and we're not trying to relearn those situations, but in this case, the answer would be -1, evidently. Now, I'm giving you examples from the book. This example is 1 and 2 from the book that's up here on the board. How can you get a -1? I thought it was area. And we just got a -1. Well, I didn't put the graph up of this function. What's this function if we're in the negative area? If, in other words, if I'm graphing this and the places I'm graphing it are over here, then this function, if x is negative, e to the x is always positive. If x is negative, the integrand is negative. So what's the graph going to look like? I don't know, but it's going to be down here. And therefore, the integral is not going to be area. This is not probably a very good picture of this, but the integral is going to be this region, which is area with a minus on it. You know that. Okay, so we don't always get area, even if we want to interpret this thing as area. Sometimes we might get negative area, whatever that is. Okay. Well, we've got one more problem. We've got several problems, actually. One more in the next 2 minutes. What do you think this means? Now, I think if you think about it, there are 2 things you can come up with without knowing which one is correct, or maybe they're both correct. Let me write down 2 ideas. Sorry. I'll get to that. One idea might be to split this thing up into 2 pieces, because we just define things in two different things. And one thing to do might be to say, okay, I'm going to split this up. The other thing that might happen might be this. Do you see that this might be a way to do it? Go the limit from t as t goes to infinity from minus t to t. Because t goes to infinity, so minus t goes to minus infinity, this would do it. Okay? Now, if we do this one, then what we're talking about is the limit as t goes to plus infinity here, and the limit as t goes to minus infinity here. And so, now, by the way, what purpose does 5 have? Why did I pick 5? Yeah, it's a given number. Do you think it would make the difference if I put 4 here? You think that'd be the same? And why? Because when we do an antiderivative and then plug in endpoints, we put in, remember the bottom endpoint is minus, you know. But if we do that, it turns out when you go the other way here, it's on the top. So here I'd be adding in something and here I'm taking it out. And so one can prove that it doesn't matter what you put here. Okay, you guys seem to just feel that's okay. And it's so what we normally do is we put a here. instead, and A can be whatever you choose. A lot of times it'll be 0. Why do we put 0 in? Because a lot of times when you evaluate something at 0, it gets simple. You evaluate it at 5 and it might be complicated. So you might add and subtract it, but who wants to add and subtract something crazy if you can add and subtract something easy? Okay. So I guess I should be over here so everybody gets to see me gesturing and doing everything. Anyway, maybe you're happier if I'm not in the picture. Which do you think is it? Or do you think they're equal? If we voted, just for the people in the room here, would you vote that these are equal or not? Not equal? One, well, how many say equal? We got 2, 4, we got 8 people in the room. One, two, I'm sorry, again, equal is like 5 out of 8. And not equal, how many would say not equal? And that's, somebody didn't vote. How many don't know? And all the hands ought to go up. Okay. Okay. It turns out these are different, not the same. And therefore we have to choose which one we mean. Remember I said this is a symbol. And you have to define what it means. And it's defined to mean the top one, not the bottom one. It turns out that what you want, this one, what happens here by doing this symmetrically, sometimes, see, when I'm doing this, remember things grow. And things might grow at different rates, positive and negative. And when you are doing it symmetrically, you might sort of mess that up. Okay? So that's not a proof or anything, but this has a name. This is called the Cauchy principal value. So, in other words, it comes up enough that it has a name and it has a use, but not for us in this chapter. Okay? So this is not, if you're given a problem like this, you do it like this, not like this. And this may have some other things that you do, but we're not going to be studying those other things this semester. Okay? So I'm going to erase that one. I don't even know if it's in the book. Doesn't matter. This is how we interpret the one with double intervals. Okay? Now, these are all improper integrals of type 1. And there may be some other name that people give them as well, but that's good enough right now. The point is, it's a certain kind of limit that you do when you have an infinity at one end or both ends of the integral sign. Okay? Now, we're going to talk about something different. Yesterday, you remember, we talked about, we didn't, but I did. We talked about a graph from -1 to 1 of 1 over x squared, if you remember. And that had a different problem because I went ahead and acted like I could integrate it and did it and got a negative number to a positive function until something wrong. And the problem is that this function is unbounded. So it turns out that if I wanted to integrate from -1 to 1, that symbolism, which has been good for us for a semester, no longer has a meaning. Why does it not have a meaning? Because the integral does not exist. But you don't even get that far. In a Riemann integration, the function you integrate has to be bounded. And this function is obviously not bounded. And therefore, we don't even get to the place to put an integral sign with this in it. In other words, when you write this down, you're making no sense in terms of what we have done so far. But if I want it to make sense, now remember, when we used a regular technique on it, it didn't work. But that doesn't mean I can't use it in some other sense. It just means I can't evaluate it that way. Okay? So that means if I want to use this symbolism, I'm going to have to redefine it. And this is an improper integral of the second kind. It's still improper, but it doesn't look improper. In the sense that when you stare at it, it looks like the stuff you've been doing forever, and you're used now to doing more antiderivatives than definite integrals. And so whenever you do a definite integral, you probably think, oh, now I have to evaluate the dumb thing at both endpoints. And maybe that's not as pleasant as just going on to the next problem. Sometimes you just put a plus C on problem 18 and go to the next problem 19. Now you have to put in the two endpoints. You know what I mean? So if you've had that feeling, like it's easy to do, I just don't want, I mean, when I stick the numbers in, it makes it, I got to do arithmetic and stuff. Some people don't like that. They'd rather have a plus C. Okay. Well, you can't do this problem the normal way. Therefore, you've got to put into your memory bank somewhere that sometimes these integrals are not proper. If it's proper, what you do is find an antiderivative and stick in endpoints. That's the fundamental theorem of calculus. But if it's unbounded, you can't do that. You can do it, but that's why you take the class twice. Okay, because I will see that and say, no, you're a bad person. Okay. So I didn't mean to look at you when I said that. Somebody looked up, I glanced and like, are you talking to me? Well, it looks like it. No. Anyway, so how do we define this thing? Okay. Well, let me ask you another question. Suppose I want to go from -4 to 4, and I have x minus 1 and x minus 3. Proper or improper?
Proper because it doesn't like.
I'm sorry.
That would be proper, wouldn't it?
Proper? I don't know.
No.
Is it bounded? What happens near 3? What's the graph of this look like? Now, you guys all can, if you want to, graph these functions. How do you graph these functions? You know, you take derivatives, you find out where it's increasing, decreasing, maximum, minimum. You can make a graph of this function. The graph of 1 over x minus 3 times x minus 4, if you graph it, it's going to have trouble at 3 and 4. It won't have trouble afterwards, and it won't have trouble before that. But this is a rational function, and you guys are supposed to know by now that we're going to have trouble at 3. It's going to go to plus or minus infinity on both sides. It might be U-shaped like this. It might be like this. It might be like this. I don't know. That's not trying to be thinking about it. Just that's the kind of stuff it does. Unbounded, improper. But now we got two problems. We got an unboundedness at 3, and we got an unboundedness at 4. That's worse than just this one, which only has an unboundedness at 0. Right? Okay. So how are we going to define this stuff? The answer is, wherever the problem is, if I want to define this, it's going to be the limit of an integral plus the limit of an integral, just like that improper one of the first kind. But, and we're going to put the integrand in here. Okay, going to have an integral and an integrand. Now, I told you if I'm going to put x here, I've got to do something else here. So I got, oh shoot, I got to remember to do that. Now I remember to do it, but you won't. And so you've got to erase it and put something else here. What am I going to do? I'm going to let, well, in this problem, 1 was not the problem and -1 was not the problem, right? The problem came at 0. So we want t to go to 0 from the left. And over here, we want t to go to 0 from the right. Does that make sense? Well, you see, what we're doing is we're saying, in one case, one integral is going to look at these areas as t goes to 0 from the left. In the other case, we're going to look at these areas as t goes to 0 from the right. I think if you think it out and draw a picture, it makes sense. So this is how we do it. We divide it up. Now, so when does this improper integral exist? And the answer is both of these have to exist. Now that's kind of good news, because that means if it's not going to exist, it's going to fail one or the other. If you pick the right one to test, you don't have to do 2. Now, how do you do this problem? You do an antiderivative. And it's the same antiderivative. So the work of finding an antiderivative is the same. You stick in endpoints afterwards, that's the same. They're different endpoints, but it's the same process. And then you take limits. Okay? Now, I would suggest that most of us would rather take a limit to a positive than these are all negative numbers. And so I think you test this one first. And what you're going to find out is this one doesn't exist. Let's see. So if I do this problem, the antiderivative is -1 over x from t to 1. And that's -1 over 1 minus 1 over t. So I get 1 over t minus 1 as the integral, the antiderivative. Then I need to take limits as t goes to 0 from the right, all the way down here. When you do this, you don't want to be sloppy because you want to be able to review this stuff later. So take the time to write it out right. And now t is going to go to 0. What happens to 1 over t as t goes to 0? Infinity. So this does not exist. Or if you like, you can say plus infinity. So this integral goes to plus infinity, does not exist. The original problem diverges. Okay? But the hardest part about this is that it doesn't look bad. It looks like something you've just been working on the last few weeks integrating. The trouble is it's not proper, it's improper. And if you evaluate it as a proper integral, as I showed you yesterday and a couple of days ago, you get a crazy answer sometimes. You might get what you think is a nice answer. It's still wrong if the integral doesn't exist, if it's unbounded. How do I do the second one? The second one, what I'm going to have to do, well, I erased the thing, but the second one's got problems at 3 and 4. So what I'm going to have to do, I'm going to have to have an integral. Now I'm just going to write down things first. This is still improper, but we can write this. I'd have an integral from -4 to 3, plus an integral from 3 to 4, plus an integral from 4, sorry, I beg your pardon. The problem was at 1 and 3, right? Yeah. So, said it wrong. -4 to 1, 1 to 3, and 3 to 4. Okay. Now, I hope I wrote 1 and 3 correctly on the other picture. Anyway, the problems were here at 1 and 3, not at 4. So this one right here is going to be a proper integral because the problem, or is it? Maybe not. Does this have a problem at either end? There's a problem at 3. It's improper too. This one's improper. What about this one? It's got problems at both ends. Shoot. So I'm gonna have to take this one and make it 1 to 2 and 2 to 3, you see? Because it's got lots of problems. And I got to approach from the left and right like I did earlier. Do you see? You got to divide it up so that at each place where it's improper, you take care of that limit. So what if we have something like 1 over t squared one way and someplace else, you know, we go to infinity this way, and I'm trying to get at is, what if we have both kinds? Then you got to split them up. In other words, if I have something going along here and it does this, okay, or whatever, the point is I'm going to have one improper integral over here. I'm going to have to cut it off someplace before it gets in trouble for unbounded. I have to have another integral that goes from the left to take care of that, another one from the right. In other words, you might have a combination of type 1 and type 2. And all of them have to exist in order for the whole thing to exist. So what's going on? Well, we have just almost covered the last section. What the book does is it does several examples, and there's one more thing the book does, and that is something with inequalities. So let me read you.
Can we pause for a second?
I'm sorry?
Sorry, I need to ask you a question.
Yes, please.
So for the 1 over x squared, it's
Slow down. 1 over x squared.
Yeah, so because one of its limits doesn't exist,
Right.
the whole thing doesn't exist.
Right. You don't worry about the other one.
Is that like?
Because we're adding, and so they don't subtract each other.
Right. I'm just like, that's the point, right? Like we're trying to figure out if okay.
Right.
Sorry.
If you split it up into several integrals, every one of them has to exist for the thing to work. And so if any one you try, I mean, if you try one that works, that doesn't tell you anything, because they all got to work. But if one doesn't, boom, you're done. So when you have a problem like this, you'd look and see, is there any one of these that looks easier than the rest of them? In other words, you get an intuition that it's not going to work, or you get an intuition that it ought to work. If it works, it's got to work for all these cases. If it doesn't work, it has to fail for one or more. So if you get an inclination that it's not going to work, you look for the one that's going to fail, because you don't want to do 5 of them. You just want to do 1 of them if possible.
So like then everything in this section is gonna fail?
Yeah.
Okay.
So, I mean, the integral will diverge. If any one of these doesn't work, then this one done. It diverges.
So then we just say.
We stop. You're done.
Diverges.
Problem's over.
How
Diverge.
do you know diverge versus converge?
Right.
Sorry.
Right. No, the answer is it does a converge, does a diverge. That's really the.
Right.
And if it converges, then you want to know to what does it converge?
Oh, so if it works.
Yeah, like I did that one thing, it had 1 minus 1 over t.
Right.
If you go to infinity, the integral goes to 1.
Right, because they both work.
When we had the 1 over t squared from 1 to infinity, this actually went to 1. We would actually write equals 1.
Gotcha.
Because the limit is 1. I mean, when I cut it off, it's this. When I take the limit as t goes to infinity, this goes to 1. And so we say the improper integral of type 1 converges to the number 1.
Because it passes. It does the integral thing.
Well, this is the integral thing.
Yeah.
This integral equals 1. That's what you say.
Right.
And you go to the next problem.
Right. Because it does all of its integrals add up like to something.
Well, in this case, it was only 1. In this particular problem I started with that had an answer, there was only 1 integral.
Right.
because we weren't splitting it in. Okay, so when you're going to infinity, like if I just start here and go all the way to infinity, there's only going to be one integral. When I go both ways, there's going to be two integrals. And in this case, this one's going to make sense, because we already did it. Do you think this one's going to make sense?
Wait, didn't that one not make sense?
This one, when I had x squared here,
Failed?
I'm sorry, I beg your pardon. I'm trying to help you. When I'm going to zero, neither of them exists. If I were going to infinity, when I look at this, I'm thinking in my head as an example to help you. If I'm going this way for both of them, and if this one didn't have a problem, okay, then they both exist.
And then they would, yeah.
Yeah, and then you'd add them up and see what you get. Now, this problem is not going to work going to infinity or not, because it's going to fail here.
I'm sorry.
Yeah,
I think I just
no.
lost it. I was like,
No, and I'm repeating things for people at home because I don't know if they can hear.
okay.
Okay? Anybody at home have a problem? Well, I don't want to hear you. Like my mother said, no, I don't care about that. Okay, there's a comparison theorem on page 573. And so it makes sense. I mean, it's sort of one of these things like it's, yeah, you all agree with it once I state it. And it's basically saying, okay, suppose I have two functions, and I'm going to look back to make sure which one is in the book. F is first, I guess. No, not the way I just wrote it. The way I just wrote it, g of x is smaller than f of x. Now the book writes it backwards. Okay, the book says f of x is greater than g of x and so on. So I use less than, the book uses greater than. It doesn't matter. And this is true for x greater than or equal to a. So we get in our minds an idea that I've got two functions starting somewhere. Now, it doesn't necessarily say a is positive, just says a is somewhere. But when we draw stuff, a lot of times you draw that. Anyway, so from here on, I know something. I know the graph of one is below the graph of the other. Now, I'm not drawing it yet because I'm going to go back and look and say, are these things continuous? Are they integrable? Are they differentiable? So on and so. Both of them are continuous functions. Okay, so if I draw one, if they're continuous, let's say this is f. And then what about g? Well, g is going to be somewhere else, but it's got to be below at each x. That's what this says. So now I got two continuous functions, fine. And, oh, by the way, suppose the function's only defined up to 5. Then you can't go to infinity. In order to go to infinity, the function has to keep going. So the domain of these things has to be, if you're doing a type 1, it has to be infinite. Okay? Okay, so I'm just looking to see if it's 33 after, remember a couple of days ago. Okay, so part A says, if the improper integral of f converges, then the improper integral of g converges. So does that make sense to you? When I do an integral of f from a to infinity, okay, if this makes sense, what about this smaller one? I mean, I think intuitively you just believe it makes sense. This ought to have a limit if this one does, if we're talking about area. Smaller number, smaller. What do you get? You either get something, you get infinity. If this one's smaller than infinity, then the smaller one ought to be smaller than infinity. So I think intuitively it's like, yeah, I go along with that one. Okay. Now, what if the smaller one diverges? Then the bigger one diverges. Yes? Do we, if we know A, do I know B? If F converges, then G converges, the intervals. What's the contrapositive? Remember the contrapositive, you switch the two parts and you put F and then switched and you put knots on both. So the contrapositive of if F, the integral of F converges, then the integral of G converges is, if it's not the case that the integral of F converges, then it's not the case. Or did I say, I got to turn both around, right? Some of you guys never got the test right. If P, then Q, the contrapositive is if not Q, then not P. And if you look into it, B follows from A. It's the contrapositive. It's the same statement logically. That just saved us half the work of proof. So that's why we review it in August. Now, how does he use this? He's got e to the minus x squared from 0 to infinity. So the author said, okay, I want to talk about this thing. Converge or diverge. The trouble is, I mean, I can write this as limited. I can act like I know what I'm doing. All right, I can write this as 0t, e to the minus x squared dx. So I'm going good here. Okay. Now I'm stopped. Because try as you would like to, you'll never be able to find an antiderivative of this, because the antiderivative of this is not among the 40 functions we know. And therefore there's no function to stick up there with a name to say it equals plus c. This is one of those functions we can't integrate in terms, meaning we can't find an antiderivative to stick in there for an answer. So the process stops because you can't evaluate this thing. Okay? But suppose that this function is small. Suppose this is the function g. And I can replace this integrand with a bigger function. And the bigger function converges. Then I can prove this one converges without integrating it. Does that make sense? So what we do is we try to majorize the function. We try to make some bigger function that has the right properties that we're looking for. And so the author looks around and he says, what about e to the minus x squared compared to e to the minus x? Which one's bigger if x is positive? Or which one's smaller? Which one's? If you're graphing these, which one do you, they're not equal, so which one do you put under the other? Well, one thing you do is plot a couple of points, okay? One won't help you. Well, what will 2 do? What's e to the minus 4 compared to e to the minus 2? This is smaller. So we can verify that this is true. Now, can you integrate e to the minus x dx? I hope so. It's minus e to the minus x. So you replace one function by a bigger one. You find out what this one is. Now, what if it's infinity? Then it tells you nothing. If the bigger one diverges, it doesn't tell you anything. It's when the bigger one converges that tells you something. So you want to pick something that if you believe that this one converges, this one, then you want to replace it by something bigger that converges, and then that will do it for you. And when you compute this one, so the example 9 in the book, when you do this one, you'll find out it converges. And therefore, this one converges. And now we have done this section. That's what's in the section. So I will be putting stuff in WebAssign on this section. And that finishes the chapter, except we skipped a section. Okay. Now, It is 20 after, so I can't even give you much help in